Welcome in this video. We are going to implement multiplicative filter networks. So although neural networks are very good at modeling high dimensional and complex signals, they sometimes struggle to modeling lower dimensional signals, such as, for example, an image or a 2D scene. If you take a standard neural network with ReLU activation function, and you train the neural network to model this image, that means that the neural network takes as input the pixel coordinates of the image and predict the color for those pixels, you will get a very blurry result because standard neural network are biased towards learning low dimensional signals. And in this case, a very high dimensional signal, and therefore we need to do something about that. For example, there is the Siren paper that alleviates this by using other activation functions than the ReLU, and we've implemented that in a previous video. In this video, we are going to implement GaborNet. So although Siren was a very nice paper with very good results, you can see that GaborNet converges much faster and gives much better results than the Siren paper. So in this video, we are going to implement to re-implement Siren and to also implement GaborNet and produce this figure. Okay, so basically a standard neural network is a function like this. So it can be written as a recursion, where for each layer we have sigma, so the non-linearity, times w z plus b, where z is the output of the previous layer. So okay, a standard neural network, very basic. And then we have the architecture that the author of this paper proposed. So in this now a layer is wz plus b, so there is no more linearity. And then there is an element-wise multiplication with g of x theta. So g is the Gabor network. On the benefit of that is that now the nonlinearity is in g, and therefore if we have a look at what is said there, okay, we never apply a nonlinearity to the output of a previous nonlinearity. So basically, I will not go into more detail, but this is really the main takeaway of those equations. And I invite you to read the paper in more detail. But yeah, we will implement that in this video, and you will see that we'll get those results, and we will therefore beat Siren by quite a huge margin. And that can be interesting for other applications. So that's always interesting to keep this in mind. For example, that neural network are biased in some ways. Okay, so for now we are just re-implementing the Siren paper just so that we can compare the results of both architecture. So the Siren is very easy. It's just this is basically the activation function for Siren. So the sign of w of x modulated by some frequency. So basically this is something that replaces the ReLU. Instead of having a ReLU of x, we have sine of x modulated by some frequency. And then the Siren architecture is very similar to a sequential MLP. We have a succession of linear layers, and then we have the sine layer as activation functions. For Siren, we need to be careful about the initialization of the weights. If they are not properly initialized, your neural network will not converge and will be stuck in a local minima. Okay, so this is the sine layer that we've implemented in another video, and I gave more detail in a previous video if you're interested in the Siren architecture. But now let's focus on the Gabor network. So first we can create a Gabor filter. So the Gabor filter is the function g that we saw there. And basically, if we go down, it's very simple. So basically, this is how g is defined. So there are a few learned parameters. So there is gamma, that is learned parameters. There is mu, there is w and phi. So basically wx plus phi, it's just a linear layer. And then on top of that, we have gamma and mu that is to be learned. So we can define the parameters mu, gamma, and then there are the parameters w and phi that are hidden in PyTorch by this linear layer. So basically, this linear layer will model wx plus phi. Okay, so also for the Gabor filter, we need to initialize the weights properly. This is explained in the paper. And now we can therefore override the forward function for linear layers for modules in PyTorch. So the first thing to do is to compute the norm. So the norm is x minus mu squared, so the L2 norm between x and mu. A naive way to implement that is just to call torch.norm, so the norm between x and mu. So first you take the difference between them, you take the square of it, and you take the norm. If you do that, you will have the memory of your algorithm will explode. Yeah, because you can do the maths on there will be some broadcasting, and that will create tensors with very high dimensions. Another way to do that is just to rewrite this operation. So if you rewrite it, that will be x squared plus mu squared minus 2 times x multiplied metrically by mu. And if you do that, there is no more broadcasting, and you don't need to store the results, intermediate results, and therefore the memory will not explode. This is very similar to the Jacobian vector product when you compute in the backward parts of some neural networks. So this is a trick to reduce the memory footprint of your algorithm. So once we've computed the norm over there, we can take the exponential of the norm multiplied by minus gamma divided by 2, and then we can also multiply it by sine of this linear layer. This is what is done there, torch.exp of minus gamma over 2 times the norm times the sinus. Okay. So now we are done with the Gabon filter, so the function g, and now we can put them together. We can have a recursion with multiple Gabon filters, and we can implement the main recursion that was specified in equation 3. So we can now implement that. So it's like a neural network with a given number of hidden layers. So by default we use k, which is number of hidden layers. We use 4 hidden layers. Okay, so we create the Gabon filters. So we have a list of k Gabon filters, and then there is also those linear layers that we need to store, and we make a list of 4 linear layers. Again, we need to initialize the weights of those linear layers appropriately. And once this is done, we can override the forward function. So we just implement the equation 3 recursively. This is similar to a sequential layer in PyTorch. Now we've done the most difficult part. Now we can implement the training function. The training function is very easy. It's just supervised learning. The input is the pixel coordinates, and the output are the color that we need to predict. And we also log the PSNR to know the PSNR over time. So just a different metric than the rest. Once this is done, we can put everything together. We can create the Sci1 model, the Gabon network model, so we can compare them. We can create the data. So the target is the RGB pixel colors of the camera data, which is a well-known image to benchmark vision algorithm. And then we can create the inputs, so the pixel coordinates. So we choose a coordinate system where the pixel goes from -1 to 1, and therefore we create a grid with pixel values. And then we can create a figure, the figure that I've shown in the beginning of this video. And then we can iterate over each model, so the Sci1 model and the Gabon network model. We can create an optimizer. You see that the learning rate depends on the algorithm. So for Sci1, we'll use 1e-4, and for Gabon networks, we'll use 1e-2. And then we can call the training function to train the model, and we can show the results. So the image that has been that is modeled by the model, and we can also plot the PSNR. Then we just improve the figure by removing the ticks, removing the axis, and saving the figure. Okay, if you run this code, you should get this figure or something that is similar to it. I hope this video was helpful to you, that it will help you in your work, that it will improve your machine learning skills. If it was, please leave a thumbs up and subscribe for more videos like that.